Hi everyone, welcome back to the channel. And if you're new here, I'm Ryan, a Cambridge educated mathematician and ex-step marker. By now, hopefully you're starting to hear back from some universities with some offers, so I hope that's all going really well. If you've got an offer from either Cambridge or Warwick for maths, they'll often put a requirement on STEP. They'll often ask for a 1 in Step 2 and Step 3, but some other university courses might also ask for it, such as natural sciences. Now, if you don't know what STEP is, I've done a video on it before, so it should be linked up above. Today we're going to be diving into some Step 1 questions, with a little bit of a twist. I won't have attempted these questions beforehand, so we'll be doing them both together in real time. Now, we're starting with Step 1 because this is what I generally recommend. It's not an official exam anymore, but it's a real good jumping on point for starting with STEP. I'm going to be pausing at key moments to give you a chance to pause the video, attempt the question yourself, and have a good think about the questions. This is a great point to actually test your skills and see how you can attempt some STEP questions. If you're ready for the challenge, grab a pen, grab some paper, and let's get started. So to start with, hopefully you've seen my last video which talks about how to get started with STEP papers and pick the right questions for you. If you've not seen it, it should be linked above somewhere. I recommend watching that before starting this video. But I've already done that, and here I picked out a couple questions that we can attempt so that we can do them together. Okay, so here's the first question. Question 2 from the paper in 2013. I'll give you a few seconds to pause the video and have an attempt of it for yourself. Okay, so a bit of the thinking about why did I actually pick this question? Well, they're introducing a new topic to me here. It's this notation that tells me about denoting the greatest integer less than or equal to x. So they'll give me a few examples to explain what it actually does. But here they've introduced that to me, and what I often say is that sometimes when they're introducing a new topic to you, it makes it a lot easier to have an attempt at that question because they often go in a bit easier on those questions. And they give me a few examples to explain it. So here they've got 2.9 goes down to 2 and minus 1.5 goes down to minus 2. In maths we often call this the floor function, but here you don't need to know that. So first off, the first thing I want to do is think about which different questions are they asking me. So in part I, there's only real one question, which is about sketching this graph here. Next, in part 2, by considering line y equals 7 over 2 on your graph otherwise, solve the equation f of x. So that's the first question here, solve this. Next, solve also for the equations of this. So they're asking me to kind of repeat what I did above, but for two different numbers. So there's kind of 3 questions within that part. And again, on this last line, there's only one question. Find the largest root of the equation f of x equals 9. So that is the only bit of that question. And then actually, even though they've not labelled it as a part, there is another question at the end, which is give necessary and sufficient conditions in the form of inequalities for the equation f of x equals c to have exactly n roots. So this last bit is also another question. So there's actually 1, 2, 3, 4, 5, 6. 6 different questions within this whole question. Okay. So next we want to think about how does one lead on from another. So looking at this, well, they've asked me to sketch this graph between minus 3 and 3. So that's pretty straightforward. They just want me to sketch the graph. Next, they want me to use my graph to solve this equation. Okay, so pretty much what it's going to be is use my graph, kind of think about what does the line of f of x equals 7 over 12 look like? Where are the intersections? How do I solve that? It's going to be the exact same for the other 2 parts of that question. It's just going to be different numbers that I have to try and solve. And then for part 3, they've slightly changed it here because I'm not now looking in the limits minus 3 to 3. I'm looking in the all of x. So they've asked just me to find the largest root of this equation. So I'm going to take something from part 2 on how I solve part 2 and apply it for when I have integers bigger than 3 and less than minus 3. And then finally, in this last part, I'm going to have to notice something because they want me to generalize it for any c. So it's essentially asking me to show that I have n roots for a value of c. So I need to kind of pick up on what I'm doing in part 2 and part 3. Okay, so now let's get into it. Let's start and actually have a solve of this question. Okay, so to start off with, let's sketch the function. Let me start and label it off by question 2i. Okay, so first off, they want me to sketch the graph. So they want me to sketch f of x equals this over x. So this floor function over x. I'll just refer to it as the floor function because that's easier than just referring it to it as this random notation. So what we then want to look at is, what does this function look like? Well, is it going to be continuous? Not really, because you can think about, if I'm at x equals 2.9999, then it's going to be f of x is going to look something like 2 divided by 2.9999, whereas as soon as I go up to 3, f of 3 is going to be then 3 over 3. So it's going to go from something not equal to 1 suddenly straight to something that equals 1. So I can kind of think about that, and I can think about sketching it like this. Just as a note, it's always going to be positive, because when x is negative, we can have a negative divided by a negative. So it's going to look like something along the lines of this. Okay, so this is x along here, and then this is f of x. As a note for these kind of questions, we want to sketch it pretty accurately when it comes to step, because often an accurate sketch helps us draw it a lot better. So first off, I want to think about, let's make it easier for ourselves. Let's do between, let's start off with 0 less than x less than 1. And I can actually do less than or equal to, because the floor of 0 is still 0. What does my equation look like? Well, my equation looks like f of x equals 0 over x. Well, that's just 0, so I'm left with just, as to draw it in red, let's plug some numbers on here. Let's say this is 1, this is 2, this is 3, this is minus 1, this is minus 2, this is minus 3. Then between 0 and 1, we just have 0 here. Okay, so then let's go a bit further. Let's go between 1 less than or equal to x less than or equal to 2, then f of x equals 1 over x. Okay, so at 1, that is equal to 1. So like this. Well, I'm just going to label this as 1, 2, 3, etc. So between, and then as soon as we get closer and closer and closer to 2, this approximately goes to a half. So we end up somewhere about here. And it's going to look like a 1 over x graph, so it's going to look like this. And just as a bit of notation, when we're looking at equations like this, because we never actually get equal to a half, we kind of just get closer and closer to it, we would leave that as an open circle like this. So at 1, I've got a closed circle. As I get to 2, it's normally an open circle. Okay, so I've done that part. Now I need to go a little bit further. So 2 less than or equal to x less than or equal to 3. It looks approximately like f of x equals 2 over x. So again, it looks like similar to a 1 over x graph, but now we're at, when x equals 2, we're actually at 1 again. So we jump back up to here. So you can kind of see that there is a discontinuity there. And again, as we get to 3, we go down to 2/3, which is here somewhere. So it's gonna look like this. Okay, so what does this look like? It's starting to trend downwards like 1 over x graph, but after the first one, it's then not going as far. So originally the first one went down to a half, next one goes down to 2/3. Interesting. What about the next one? 3 less than or equal to x less than or equal to 4. F of x equals, what is it equal to? 3 over x. Okay, so again, starting at 1, let's jump up, back at 1, and now when we get to x equals 4, we're going to 3/4, which on my graph, badly drawn. I actually don't need to draw this, just even realised now. It looks like this, but I don't need to draw that, so, but still actually not bad information for me. I'm seeing that it's going less far down every time, but actually what I can do is get rid of this. And in the question they asked for between -3 and 3 inclusive. So I've got to include this dot at 3 because that's where it is at x equals 3. Okay, so I've done between 0 and 3. Now let's go backwards. So between -1 less than or equal to x less than or equal to 0, we have f of x equals, what will it be equal to? It will be equal to -1 over x. Okay, so it looks a little bit different because it's now -1 over x, but we're in the negative region. And if I remember right, what does 1 over x in the negative region looks like this. So therefore, -1 over x looks like this. But I'm again not sketching the whole region, but I can see a trend there. I can see what it's going to look like. So between when it's at -1, it's going to be equal to here, and then as we get closer and closer to 0, it's going to go up like that. Okay. Oh, my bad, misdrawn that because that was not at 1. Should have been there, and it goes up like that. Okay. So next one is -2 less than or equal to x less than or equal to -1. Then f of x equals -2 all over x. Okay, so then we've got, it goes between, again it goes from x equals -2, it is here, and then as we get close to -1, this goes to 2. So it's going to end here. It's going to look like that. Okay, discontinuity there. And last but not least, -3 less than or equal to x less than or equal to -2. Then f of x equals -3 all over x. Okay. Okay, so again starts at +1. And it goes up to, what does that go up to? When we get to 3 over 2, so 1.5. So it's going to go to about here. Look like that. Another discontinuity there. Okay, so on both sides, what does this look like? On both sides, we're getting kind of these repeating patterns, but each time it's not going as far. You can see it between 1 and 2, it goes between, between 1.5. Between 2 and 3, it goes from 1 to 2/3. And then, as I've already drawn, between 3 and 4, it goes from 1 to 3/4. That's in the positive side. On the negative side, between -1 and 0, it goes from 1 to infinity. Between -2 and -1, it goes from 1 to 2. And then -3 to -2, it goes from 1 to 3 over 2. And I can imagine that the next one, -4, will go from 1 to, what will it be? 1 to -4/3. It'll go to 4/3. So it will go less far up. Okay, that's interesting. Weird graph. Okay, cool. So that's part 1 done. Okay, can we now go on to part 2? So consider, is it y equals 7? Yeah, y equals 7 over 12. Okay, I'm going to draw this on my iPad, but being on an iPad, it's easy to rub out. But what I'd suggest is just make it so that it's easy for you to rub out, because we're going to have to do it again for 17 over 24 and 4 over 3. But I'm pretty glad I drew this well, because I can kind of see what's going to happen here. I'm going to intersect some of them, but am I going to intersect all of them? Okay, so 7 over 12 is just above a half. Is it above 2/3? No, it's not, because 2/3 is 8 over 12. And if you remember, this bit here is 2/3, whereas this bit down here is a half. So it's going to go in between them, if I can draw well. And on the left-hand side, it's just going to hit nothing. So the only solution I'm going to have is this one here, the one between 1 and 2. So what I actually need to solve is the equation of that little bit, which was an easy equation because we developed it up here. We have f of x equals 1 over x. Okay, so then we need 1 over x equal to 7 over 12. Therefore, this implies x equals 12 over 7. Okay, cool. So Yeah, and that makes sense because that's between 1 and 2, which is, as I expected, somewhere between 1 and 2. Okay, not too bad. So I'm actually going to label this as 2 part A because it makes it a little bit easier. Okay, so then part B, which is consider y equals 17 over 24. Okay, so let me just erase these so I can continue my sketch. So now, if I draw the yellow line, okay, so where is 17 over 24? 17 over 24 is, it is bigger than a half. It is 2/3 would be 16. So it's, and 3/4, if I had that on the graph, which I don't, so I don't need to think about it, but 3/4 would be 6, 12, 18, 20, 6, 12, 18. So it's somewhere between 2/3 and 3/4. So now if I draw that on the graph, it's going to be somewhere around here. Okay, so now I've got 2 solutions. Cool. So I need to solve it twice. Oh, did it mention? Oh, it didn't say that I had multiple solutions. That's interesting. But I'm pretty confident I have multiple solutions. But it's always a double check. If it says find the solutions, then I'd be pretty happy with the fact that I have multiple solutions. Okay. So, but what I now need to solve is that I need to solve it between 1 and 2 and then 2 and 3, which have different equations technically. So first we need to solve, so let me write between 1 less than or equal to x less than 2. We need to solve 1 over x equals 17 over 24, which implies x equals 24 over 17. Okay, that's one solution. And then between 2 less than or equal to x less than 3, we have actually the equation from above was 2 over x. So I have 2 over x equals 17 over 24, which means that x equals, well, it's 48 over 17. Now, just a bit of a sanity check. Does that make sense? Well, we need it to be between 2 and 3, and 17, 34, 51. Yeah, so it's less than 51, so I'm pretty happy with that. So that is my other solution. So we have 2 solutions. X equals 24 over 17 and 48 over 17. Okay, that's part B done. Going on to part C. Okay, going back up, what do I need to solve now? 4/3. Okay, so 4/3 is greater than 1. So technically now, going back to the graph, we don't actually need to think about the right-hand side. All we need to think about is the left-hand side. So 4/3, where's 4/3 lie on this graph? 4/3 is, is it dead on where I said before? I said 4/3 before, didn't I? Yes, so it's actually along here-ish. And then if I was to continue the graph, this would be the open point, so we never actually have it equal to 4/3. So we have 3 solutions now, so we need to do it 3 times. So here, here, and here. So we need to solve 3 equations. Well, scrolling back down, 3 equations we need to solve. So just let me write y equals 4/3. Okay, so the first solution was between minus 1 less than or equal to x less than or equal to 0. Ooh, less than 0, need to be sure about that. We have minus 1 over x equals 4/3. This implies x equals minus 3 over 4. Again, is in the region I'm thinking about because it's between minus 1 and 0. Okay, cool. So next, between minus 2 less than or equal to x less than 1, we have the equation minus 2 over x equals 4/3. we have x equals, what will that be? That will be minus 6 over 4. Is that again in the region I want? It is, sorry, I should have had a minus here. It is minus 1.5, so yeah, perfect. Okay, again, next one. Between minus 3 less than or equal to x less than minus 2, we have the equation minus 3 over x equals 4/3. X equals minus 9 over 4, which is just less than minus 2, so perfect. 3 solutions now. 3 solutions. X equals minus 9 over 4, minus 6 over 4, and minus 3 over 4. Okay, cool. So, next we have part 3. So we want to find the largest root of the equation f of x equals 9 over 10. Okay, so they've slightly changed this one because we're not now looking at the graph. We are looking at finding the largest root of that equation. So we want to consider f of x equals minus 9 over 10. Sorry, not minus 9 over 10, 9 over 10 itself. Okay, so what does that actually look like? Well, let me just scroll back up to the equation for a second. So, is there a way I can more generalize this for more points? Well, So, let's have a think. Well, there is a solution if I have a solution in the region between, let's generalize it. Let's say between n, let's draw a bit of the graph. Let's just draw on a section later on. 9 over 10 is less than 1, so we're just considering the right hand side. Okay, so let's call this n and n plus 1. What does this go between? This goes between, it'll start off at 1, and it will go down to n over n plus 1. So between these two values, I have a solution if the value, let's call it y, is between n over n plus 1 less than or equal to y less than 1. Less than or equal to 1. Actually, need to change this to greater than because we don't actually have this point at the bottom. It should be an open circle. So I need this to hold, and then I have a solution in that region. So this is true for any n as you continue drawing the graph as you go further and further on. I need this to happen. So let me scroll back down. And they've told me f of x equals 9 over 10. So to have a solution at between two integers, n and n plus 1, I need this to be true. N over n plus 1 must be less than or equal, less than 9 over 10, less than or equal to 1. I mean, clearly on the right hand side, that's clearly true, so I can ignore that. So what I need is for this condition to hold, and then I have a solution for that n. That will tell me the largest possible value. So I have, if I multiply by 10, on both sides, I have 10n over n plus 1 less than 9. I then multiply by n plus 1, 10n less than 9n plus 9. Okay, then I have n less than 9. Okay, so if I have n less than 9, that must mean I have a solution. So for n equals 8, I must have a solution. So somewhere in the region between 8 and 9, I must have a solution. Okay, so what does the region between 8 and 9 look like? Well, the equation for that is f of x equals 8 over x. Okay, so now I must have 8 over x is equal to, what will it be, 9 over 10. So I have x equals 80 over 9. Okay, well that works, that's fine. Okay, Would it work if I went one higher, just to double check my maths? Well, if we went to n equals 9, I would have had n equals 9. I would have had f of x equals 9 over x, and that would have been equal to 9 over 10. Well, then I would have had x equals 10, which is technically, for between 9 and 10, is outside my range, because for this, I need 9 less than or equal to x less than 10. Because at 10, we're no longer using, the top would no longer be the value of 9. It would be 10. Okay, so this is my highest value. Perfect, so that's part 3 done. Okay, cool. So we've solved all of part 3. And then what I would generally do is, if I was doing this in exam, I'd make my writing a bit clearer. I've been a little bit all over the place here. I've given a condition, but I've not really talked about what that condition is, so it might be handy to write for a solution between n and n plus 1, this condition must hold. Must hold. There we go. And then I could even put a note here, we need n to be less than 9. Okay, cool. And then that's part 3 done. And now we're just left with the last part of the question. Okay, so ignoring the first little bit, which is necessary and sufficient conditions, which I'll come back to, it asks us to give conditions on this value c, for which we have exactly n roots. So scrolling back up to the image, what do we have? We have this image. So you can kind of see what's going to happen here. So if I'm less than less than 2/3, I will have exactly one solution, because I only pass the one root here. And when they say roots, that's essentially crossing points for us in the terms of the graph. So I only have one crossing point. So a condition might be that for one root, we need c to be between 1/2 and 2/3. But you'll also know on the other side, if we have c bigger than 2, we also have only one solution. So what they're actually asking us to do is, they give us a random number n, could be 7, 17, 264. I need to give conditions on c to get exactly that many roots. Okay, so then going back to the first bit, give necessary and sufficient conditions. 2 parts there. What does sufficient mean? Sufficient means if I give you a condition on c, you get what I said, you get n roots. So if I give you the condition between 1/2 and 2/3, you get exactly one root. However, that's only sufficient, so that's, I give you a condition, you get what you expect. The other way is necessary. Necessary means it's the only way to get one root. So for this, we would need the condition that c must be between 1/2 and 2/3, or c must be greater than 2, because that's the only way that we get exactly one root. That's what necessary means. Okay, so now to actually attempt this question, I'm just going to copy the graph down, because I think the graph's going to be quite useful for this. So copy, paste that in there. Okay, so let's start and do it for some smaller numbers. So I'm just going to consider the positive side for now. The neat thing about this is that I can just consider the positive, and then do it separately for the negative, because they don't overlap anywhere, so I can kind of give 2 separate conditions. Okay, so for one root, what do I need? Well, for one root, I need it to be between this point here and then this point here. And I need to be careful about my less than or equal to or greater than or equal to. So to have exactly one root, I need c to be bigger than 1/2 and less than or equal to 2/3. I can have 2/3 because that is an open circle, so it means that isn't included. Okay, so let me just write a bit of a note for the positive region. Region, i.e. c greater, c less than 1. or x greater than 0. Okay, so that's for 1. For n equals 1. Okay, what about next? N equals 2. Well, we can consider the next part of the graph. I haven't actually drawn it on here, but would come down to here, something like this. And from earlier work, that would be at 3/4. So at the minute, if I want 2 roots, I need it to be somewhere between here and here, because I would get 1 root on the first bit of the graph and 1 root on the second bit of the graph. That. So I need C to be between these 2 values. Okay, so what does that mean for C? That means I need it to be between 2/3 less than C less than or equal to 3/4. Okay, patterns starting to emerge here because I'm just going up on, I'm increasing every value by 1 essentially. If I was to go again, what would the next one be? It would be, again, starting from 1 and using the equations, it would go down to 4/5 because it's mod x over x. So at the point of 5, you're going to get, 4.999999, you're going to get 4 divided by 4.99999. So yeah, going to go down to 4/5. So again, my next condition will be that n equals 3 roots, I need 3/4 less than C less than or equal to 4/5. And now I can definitely see a pattern emerging. So for n roots, I just need it to follow the form for n equals n. I wrote a bit of an abusive notation, but it's fine. Well, for n equals 1, this was an n over n plus 1, because, yeah, less than C, less than n plus 1, less than or equal to, over n plus 2. Okay, so does that make sense? Well, let me try some of the values I've already worked out. For n equals 2, plug in, I get 2 over 3, less than C, less than or equal to 3 over 4. Works perfect for n equals 3. 3 over 4, less than C, less than or equal to 4/5. Okay, that seems perfectly good to me. That seems to follow my trend. That would be enough to get the marks in the exam. But can I actually now think about it more in terms of a more general approach rather than just looking for the pattern? Well, first off, I can have a look and I'll say, well, when n is between 1 and 2, I have 1 solution. When n is between when x is between 2 and 3, I have 2 solutions, etc., etc. So if I start and look at a bit of the graph, and I draw just a couple of the values. So I start with n here, n plus 1 here, and then n plus 2 here. What does that actually look like in terms of the function? Well, again, the function is x over x. So always starts at 1, and then it drops down to, for this one, it will be n over n plus 1. And then it's going to shoot back up to 1 and then go down to, this will be n plus 1 all over n plus 2. So to have n solutions, I need a solution in here, but not in here. So how can I actually get a solution in one and not the other? Well, C needs to be somewhere in between the two. Somewhere in here. So again, that means I need C to be greater than n over n plus 1, which needs to be less than or equal to n plus 1 over n plus 2, which is exactly what I found earlier, but this is a more general approach, thinking about how many solutions do I get for each one. Okay, cool, so that is the positive side. Now what I need to have a look at is the negative side. So for the negative region, I dot E C greater than 1 or x less than 0. I then need to look at what do I get for the different regions. Okay, so
let's start again doing n equals 1. How can I get one solution in this? Now let me rub off some of my other markings because it's going to confuse things a little bit. So for one solution, I need c to be greater than or equal to 2. I can have 2 because that would default to the first graph. So I need to c to be greater than or equal to 2. Okay, then for n equals 2, what do I need? Well, for n equals 2, I need it to be between these two values, between here and here, because that means I get a solution here and here. So I need it to be greater than this value, I believe was 3 over 2 here, and this was 2, so I need it to be between 3 over 2 less than or equal to c less than 2. Okay, n equals 3. Okay, so n equals 3, if I was to continue drawing, this would be 4/3 that it goes up to, like this. Again, just using the equation, so this would be 4/3. So I need it between 4/3 and 3 over 2. So 4/3 less than or equal to c less than 3 over 2. Okay, I might just do one more because I'm struggling with the pattern a little bit because I've got 2's in there. It's confusing things a little bit, but I think I have an idea. But the next one, again, would go up to 5 over 4 and then back down. So I need c to be greater than 5 over 4, less than or equal to c, less than 4/3. Okay, again, patterns emerging. I'm increasing this by 1 every time. So 3 to 4 to 5, 2 to 3 to 4. And the reason why it's a bit more difficult to see is because we've wrote it as 2. Technically, it's 2 over 1. And this is also 2 over 1. We just don't normally write the 2 over 1 because easily goes back down to 2. So therefore, I can again see the same pattern for n equals n. It will be, so what am I getting? I'm getting n plus 1 over n on that side, less than or equal to c, less than, a bit harder with n equals 1, but if I look at n equals 2, getting n over n minus 1. Okay, and then when I go back to the n equals 1 case, what's this going to be? It's going to be infinity, which is just c bigger than 2, so that works perfectly. Okay, so perfect. So I've again got a value within that region. Okay, so so I would give these as my 2 conditions. And again, you can do the same kind of argument with looking at the n and n minus 1 case, and then n minus 2, and you can get a similar general argument out. Well, these would be my 2 conditions that would signify how many roots I'm going to get. So it's all about looking at how many crossing points you're getting on the graph. So again, as I said earlier, this graph is really useful for us. On to the next question. Okay, so now we've done the first question. Here's another question that we can have a look at. So this one I picked because it was to do with differential equations, and I'm generally pretty decent at differential equations. I'm asking us to use a substitution, which is fine, but then we want to work out later on we need to work out what the substitutions are, but pretty happy with this. This is what I'd choose. So I'll give you a few seconds, you can pause the video and have a go at it if you choose. Okay, so let's first off break up the question parts. This one's pretty easy because it's just 3 questions. First part is just use the substitution and show that we can get a solution that is equal to this, y equals x square root 4 plus 2 ln x. Looks a bit awful, but it's fine. Part 2, use a substitution to find the solution of this differential equation. Again, just one more question. And then finally, again, use another substitution to find that solution. Looking at this, I can kind of see where the question's going. This first substitution will give us a hint at what happens. We're going to use a similar substitution for part 2 and then a similar substitution for part 3. You can see each time only one thing is changing. So the first and the second, we've just doubled that last coefficient. And then in the last bit, we've used an x squared instead of an x. So I can see there's going to be subtle changes about this. But yeah. Okay, so let's get into it. Okay, so for part I, what does it say? It says start with a differential equation, which I'll write down. Dy by dx equals x over y plus y over x.
not something I'd be immediately knowing how to solve because I can't use separation of variables and I can't see a neat, easy solution for myself because there's a 1 over y and there's a y. Okay, but they've told me use the substitution. Substitution. Y equals ux. Okay, so first off, I want to find out what dy by dx is in terms of u and x. dy by dx, I'm going to have to use, you're going to need to use product rule, so it's d by dx of ux. This is equal to du by dx times by x, so I've left the x alone, and then it's plus u times dx by dx, which is just 1, so I can leave it like that. Okay, so now I can plug everything in now. So I've got, back in the differential equation, I can even write that down. Equation x du by dx plus u equals, now I've got x all over ux plus ux over x. So actually those two cancel and so do them. So I'm left with equals 1 over u plus u. Oh, interesting, because them two cancel. And then I'm left with x du by dx equals 1 over u. Okay, now that's much easier for me because I now can use separation of variables. I can bring the u over to the one side, so u du by dx equals 1 over x. And now, using differential equations, I can integrate both sides, and I will have integral of u du equals integration of 1 over x dx. So a half u squared equals ln x, always remembering constant of integration. They've given me no limits, so, well actually they have given me limits, but I'm not going to use them yet. I'm first going to plug back in for u. So u, actually, using the substitution at the start, equals y over x. So I've got half y squared over x squared. And now that is equal to ln x plus c. Rearranging a little bit. I don't want to do too much yet because I want to use those constants. Y squared equals 2x squared, open bracket, ln x plus c. And already see I'm heading towards what I wanted. So first off, not first off, I've already done first off. I'm going to use the boundary conditions. Y equals 2 at x equals 1. So now I've got 4 is equal to 2. Ln 1 is just 0 plus c. So therefore c equals 2. Pretty easy. Then I'm left with y squared equals 2x squared. Open bracket, ln x plus 2. Okay, then just square rooting. Y equals x, and then I'm going to bring the 2 inside, just makes it a little bit easier. Square root of 2 ln x plus 4. Hopefully that's what they asked for. It is perfect. Okay, so that's part I. Wasn't too bad once they've given me the substitution. Seemed to all work out okay. I noticed that things were cancelling. So I'm going to notice in the next two parts, I want one of the terms to cancel. And not super obvious yet how that's going to happen, but I'm going to give it a go and see. So now moving on to part I. So I've got now dy by dx equals x over y plus 2y over x. Okay, so I noticed in the last one that this y over x cancelled. But if I do the same thing again, if I use y equals ux, it's not going to cancel because I'm going to have 2 of them rather than just 1 of them. So I'll have a 1 over u plus u. It's not generally awful. I could use it. It would be fine. You know what? Yeah, let's go for it. Let's try. So let's say y equals ux. See what happens. Always in the exam, try it, see what happens, see what doesn't work, and it might give you a bit of a hint. So y equals ux, similarly before, dy by dx equals x du by dx. I'll just write substitution here just so I know what I'm doing. Substitution plus u was at the bottom. Then I've got x du by dx equals, and then I had it was x over xu plus 2y over x was ux over x. Those cancel as before. Oh, sorry, there should be two of them. You forgot. And there's also a plus u on the side. So now what I've got is x du by dx plus u equals 1 over u plus 2u. Okay, so rearranging again, x du by dx equals 1 over u plus u. Okay, so again, I can use separation of variables. It's not as neat as it was last time, but I can still use it. So therefore, bringing it all over, 1 over u plus u du by dx equals 1 over x. Gonna have to neaten this left hand side. Okay, so got to this point. It's not super nice, but let me multiply by u top and bottom to neaten it up a little bit. So we've got u over 1 plus u squared du by dx equals 1 over x. Oh, okay. So I know how to solve this because it is inverse chain rule. So I like to call this integration by guessing, because you kind of guess the solution and then re-find out what it will be. So actually the solution, once I integrate, let me just actually do that, equals integral of 1 over x dx. So you end up with ln of 1 plus u squared, and then if I was to differentiate this, I'll get 2u, so I want a half at the front, equals ln x plus c. Okay, so next what I can do is multiply by 2, ln of 1 plus u squared equals ln of 2 ln x plus, I'm going to leave it as a constant c because I've just changed an unknown constant into another unknown constant, so I don't really need to change the c. Okay, want to get this in terms of just u, so 1 plus u squared is equal to e to the power of 2 ln x plus c. That is the same as, take the 2 up, so I get x squared, and then bring it down, so it's x squared e to the c, and then e to the c is just another constant that can be ax squared. So therefore u squared, which is the same as y squared over x squared, is equal to ax squared minus 1. Y squared is equal to ax to the 4 minus x squared. And now all we need to do is actually find out what a is. So at, what was the condition? Y equals 2, we have x equals 1. So therefore 4 equals a minus 1. So a equals 5. And we're left with the equation of y squared equals 5x to the 4 minus x squared, or rather y equals the square root of, bringing x out the front, 5x squared minus 1. And that's for part 2. So next we need to scroll on, and I'll use a new page for part 3. What do I need to do? I need to solve dy by dx equals x squared over y plus 2y over x. Okay, similar again, all that we've changed is an x squared, but what I'm noticing is I'm not going to end up here with a 1 over u. I'm going to have an x over u, which is going to be a pain because I now can't do I can't do separation of variables, so it's much more difficult for me to solve. Okay. So y equals ux won't work. Won't work. What else might work? What about if I just increase the x power? Y equals ux squared. Well, this term on the left will become a 1 over u again. However, this term on the right will be a ux, multiple of ux, but still ux. Oh, but the left-hand side, when I do the derivative, will have a ux rather than just a u. Oh, so this might work, I'll try it, see what happens. So dy by dx, just right here, try substitution. Dy by dx equals x squared du by dx plus u times by the differential of the x squared, which is 2x. Okay. Ooh, looking promising actually. So then we have x squared du by dx plus 2xu equals x squared over ux squared plus 2y, which is ux squared, all over x. Okay, so neatening this up, you can already see this cancels with this, makes it a little bit easier. This cancels with this, and ooh, yeah, them two cancel, perfect. So this cancels with this as a whole. So I'm left with the equation x squared du by dx equals 1 over u. Oh, so much easier now. Okay, so I'm left with du by dx u du by dx equals 1 over x squared. And then integrating this should be pretty easy. So integral of u du equals integral of 1 over x squared dx. And then I have half u squared, again, equals minus 1 over x plus constant of integration. And then after doing this, plug in u, which is now different. U equals y over x squared. So I've got a half y squared over x to the power 4 equals minus 1 over x plus constant. Rearranging for y, just because it's neater. Y squared equals minus 2x cubed plus 2x, should be cubed, minus 2x to the power 4. Okay, so then, and I should have a c there, nearly forgot. Now I need to find that constant of integration. So when y equals 2, x equals 1, so I have 4 equals minus 2 plus 2c. So c actually equals 3 this time. So I'm left with y, I'm going to do the square root at the same time, is the square root of 6x to the 4 minus 2x cubed. Okay, that is a much nicer equation than the last one. I can get y on its own, so I'm pretty much a lot happy with that one. I have a slight concern about part 2, but I would in general say I'm pretty happy with how that question went. Substitutions were pretty straightforward, and so yeah, we've now completed that whole question. So what I would do now is, because I'm pretty happy with how those questions went, I would go and look at the mark scheme, give it a mark. You can even have a look, compare my answers, see if there's anything I missed, because sometimes I do miss things, and even something like small conditions, but I believe I did quite well on this, and I'd probably get the majority of the marks. Maybe not all, but a good 18 or 19 out of 20. And that's it for today's video. How did you find the questions? Let me know in the comments if you found any interesting shortcuts or insights that made the question a bit easier. I'd love to hear your thoughts. If you enjoyed working through these problems with me, the mess that it was, please consider hitting that like button. And if you're new here, consider subscribing, consider sharing it with other people that you think it might be useful for. I'll be tackling more questions in the future in the build up to step 3, so make sure you got notifications turned on. Until next time, keep practicing, and I'll see you in the next one.